I want to mention something about the spike and slab RBM because I had some questions about it from some of you. So these were some of the samples we talked about yesterday that I consider to be amazing samples of small images at least. I didn't show the details of the model, and I'm gonna just skim the surface here. It's a variant of RBM with an energy function that has visible units as usual, but where the hidden units are split into two groups, a vector of binary hidden units as usual in RBMs, but then also a vector of continuous valued so-called slab units. And the main term of the energy function is this. So if you've seen RBMs and both machines and stuff, you should recognize this as almost the same as usual, except that we have this S stick in the middle. So you can think of SI times HI, so HI is binary and SI is continuous, as replacing the usual hidden unit contribution to the energy function. So it's basically the same thing as the RBM, except now you can think of the binary, you can think of the hidden unit as being either 0, and that's going to happen when HI equals 0, or some real value. So the usual RBMs are are usually just binary, period. And now that's also kind of interesting in light of all the things you've heard about sparse coding, because it's another way of thinking about sparsity, where the sparsity comes more explicitly not by doing map, some kind of optimization, but in the model itself, the hidden units will want to be either 0 or something continuous, and the prior probability on these hidden units will control how often, how sparse the model will be, and actually that's one of the hyperparameters we tune. So there's a regularizer on the bias of this hidden unit that will make it more or less sparse. The other terms are also interesting. I'm not going to go into them, but the main thing about the other terms is that they have these interactions between the visible. So in a regular RBM, there are no lateral connections between visible, which is convenient from a computational point of view, but is inconvenient from the point of view of modeling things like images that have lots of correlations between pixels that you'd like to pick up. And actually what you'd like to do, what you have here in the middle, you can think of the inverse covariance matrix of the visible given the hidden units. Actually the full formula is here, but this sort of is more like a precision matrix. And so depending on the configuration of the hidden units, you'll get different covariance matrices between the pixels. And so the hidden units control the mean through this usual thing, the mean of the visible. Think of this like this is saying what those guys want to be in average, and through those parameters phi, the hidden units are saying what are the covariances that are expected between the pixels. And so these are the main components of the model. And from a practical point of view, the nice thing is there's a three-way Gibbs sampling between the three groups of units, the binary units, the continuous value units, and the visible, and all three sort of updates are easy to do. So this was a little parenthesis to complete some of the things I said yesterday about spike and slab, and now I'm going to move on back to where I was. So I was talking about autoencoders, and most of the lecture today is going to be about autoencoders. So again, as we saw yesterday, autoencoders, you can think of just neural nets that try to predict their input, and we call that prediction a reconstruction, and I'll denote them as R of X. Skip this, we did this. And again, so this we saw already, but to summarize an important point about yesterday, that you can think of what an autoencoder is trying to do, or anything that minimizes reconstruction error. So this is reconstruction error. It's trying to make reconstruction errors small at the training example. So imagine this x-axis is training examples. You have an example here, you have an example here, you have an example here. It's trying to make reconstruction errors small at the training examples. And because there are some constraints or some regularization, it's going to be forced to have reconstruction error high in other places. That's sort of the basic idea of how this is capturing the structure of the density. But there's more, and what I'll be doing today is going into more detail about the sort of some mathematical results about the fact that the reconstruction function and its derivatives tell you something about the local statistics of the distribution. And you can think of training with autoencoders and basically anything that minimizes reconstruction error is doing something else than maximum likelihood, but that also captures the structure of the density using a kind of moment matching principle. Okay, so one of the reasons why we're interested in these autoencoders, even the simple ones that have a single layer, is that even though we train, only a single layer autoencoder, we can stack them. In other words, once we've trained one, as we've seen yesterday and you've seen last week with RBMs, you can use the representation learned by the first autoencoder, so this part, as an input to train a second autoencoder and so on. So you've seen this. We've done this like 6 years ago. And one thing I didn't mention, which is like a little digression here, and I've seen this being used more and more in recent papers. You can also use this trick of layer-wise training, not just for unsupervised learning, but also for supervised learning. So we in this same paper we called that greedy layer-wise supervised training. So the idea is, let's say I want to train a supervised neural net that's going to be deep. Well, because training a deep one is difficult, what I can do is train first a simple one, which has just one hidden layer. I've written it this way because what I'm going to do next, after I've trained my first MLP, is throw out this part of the model and just use the first hidden layer and its parameters to give me a first representation, and then I can train a second neural net on it. Again, throw away this part and so on, and keep adding layers as many as I want. In those days, we found that it works not as well as using unsupervised pre-training, but people recently using really large data sets have shown, like in speech recognition, that you can actually get as good results as using unsupervised pre-training because you have so many label data, or because our unsupervised learning algorithms aren't that great and we need to make them better. Another sort of little connected point about supervised and unsupervised, in this early work we used so-called supervised fine-tuning. So after having initialized the weights of a neural net using unsupervised learning, we fine-tune, we basically continue training using usual supervised criterion, stochastic gradient descent or something else. And some researchers sort of doubt that maybe weren't sure that this was necessary and sort of skip that phase. And in fact, for some problems you don't need to do it, but for many problems, especially as you have more and more label data, this supervised fine-tuning step turns out to be really useful and gives you a boost in performance. In other words, after you've done your unsupervised learning, in many cases it pays to continue training using a supervised criterion. And in this picture, we see what happens. The first 100 epochs of training, I guess, are purely unsupervised, some MLP on top of the learned representation, but without interaction with the unsupervised learning. And then at this point, we consider different alternatives. One possibility is just to continue unsupervised learning independently of the supervised objective. And the other extreme here is just do supervised fine-tuning. And you can see that as soon as you ask the lower layers to do something more than unsupervised learning, something more focused, you get a boost, and then it saturates. This is on MNIST, and this is old results from 5-6 years ago. All right, let's get back to autoencoders now. So one little point, again, that comes from a question that was asked to me in the break was, well, what should we use as the reconstruction error? So I've been using squared error as a prototype, but you should generalize in your mind to any kind of loss function. And which one? Well, it depends on the type of data, the types of variables you're looking at. So for example, when we play with binary inputs, and actually that works for MNIST, even though they're not quite binary, but you can think of them as probability for binary variables. We use the so-called cross-entropy, which is this formula. So Ri is the prediction for bit I, the reconstruction for bit I using the input x, and xi is the actual value of bit I, which could be also a probability between 0 and 1. So we think of xi as a binary stochastic variable that we observe, and we're trying to predict its probability. So this is just maximum likelihood. This is minus the negative log likelihood of the x's seen as bits given the probabilities predicted by our reconstruction. So assuming the reconstructions are between 0 and 1, like using a sigmoid. Similarly, if the x's are, instead of bits, they are, say, multinomial, so they think of them as integers. Maybe you have some of your inputs are words, for example, or symbols taken from some fixed set, then think of them as multinomial and encode them with the one hot vector. So let's say I collect all of the zeros and ones for this one hot vector into a vector x. Then it's just negative log likelihood, so we want to make sure that the probability that our model gives to the correct output, the observed value, is going to be as high as possible. And these r's should sum to 1, for example, using a softmax. And the sum is only over the one hot elements of the vector corresponding to this particular variable that you want to predict. Right, so basically you use the same principles that have been used for decades for training neural nets when you do reconstruction, except now you predict inputs rather than target variables. Okay. Let's get back to this notion of manifold learning, because I'm going to try to give an interpretation of autoencoder learning as manifold learning. So again, to summarize some of the basic things we're trying to do, we're going to assume or we're going to think of our data as coming from a distribution which concentrates in some lower dimensional region in input space. So there's a lower dimensional manifold. That would be in the continuous case. In the discrete case, what would be the equivalent of a manifold? Well, it would be simply a region in your input spaces set of configurations that has very high density, and the sort of the fact that the equivalent of lower dimension is that from any point, any of these high density points, there are only a few local changes you can make, which preserves the high probability, which make you stay on the manifold. So now, for example, if your input is sentence, you can think of, well, what can I do to change that sentence a little bit syntactically or semantically so that it remains a valid high probability sentence? Maybe change one word, for example, but keeping a similar meaning, or change, say, from active form to passive form. That would be a large change in input space, but maybe a small change in good representation space. This is just illustrating that images, most random configurations of pixels give, a white noise like this, and images occupy a very low dimensional set of points. All right. So in my introduction on autoencoders, I mentioned that it's quite important to choose a way to train autoencoders that regularizes them. It's not just in the usual thinking of regularization for the purpose of capacity control. It's because we want to make sure that the autoencoders don't learn the identity, to make sure, so it's more basic than just regularization in the usual VC sense. It has to do with the fact that we want to make sure that the reconstruction error will be high in most places. And I've listed a few ways of doing that. One of them is some sparsity. So you've seen a lot of that already. But now I'm going to talk about sort of one of the methods that I consider most interesting to do that. It's the denoising autoencoder. So what is a denoising autoencoder? It's a regular autoencoder with a twist. And the twist is that when you train the model, instead of giving the raw input as input to your encoder, you first corrupt it. So you can think of adding a little bit of Gaussian noise, or you can think of, in the case of discrete inputs or MNIST, for example, you can think of randomly corrupting, like setting to 0 or 1, some of the input bits. And you might do, and typically the number of bits you're going to hide like this might be 30%, 40%, even 50%. So you're basically taking your input and destroying it, destroying half of it, and then you ask to reconstruct the original clean input. So the reconstruction error is going to compare your reconstruction output with the raw uncorrupted input. So that's the denoising autoencoder. The name denoising tells it all. It's trying to undo the noise that you've added to your input. And in principle, you can use any parameterization, again, for encoder and decoder. And in experiments, we found that in terms of learning features, in other words, if we use this as input for a classifier and we stack these things, this is actually better or as good, depending on the data, as RBMs for unsupervised pre-training. But now let's try to understand a bit better what these things are doing. So there is an important fact to understand what these are doing, which is summarized in this little equation here. It says that the reconstruction minus the input is, this should be proportional to, but I didn't find the symbol in PowerPoint, proportional to this thing, which is a derivative of the estimated log density with respect to the input. So this thing is called the score when you estimate density. It's the direction in input space in which the density increases the most, right? It's the gradient of the density with respect to the input. Let's try to visualize what that means and see how this connects sort of naturally from a geometrical point of view with what the denoising autoencoder is trying to do. So let's think of our examples as concentrating near some low-dimensional manifold, like here. So this is our manifold. So what is the denoising autoencoder doing? First of all, we take a training example, which is near the manifold. We corrupt it. So that automatically moves kind of, in a high-dimensional space, that automatically moves us orthogonally to the manifold, because most of the directions are not directions on the manifold. So random direction tends to be orthogonal to moving on the manifold. And then we ask the autoencoder to take this corrupted input and predict the original clean input, which is on the manifold. So it's learning a function from corrupted to clean, which are on the manifold. So it's trying to map things to the manifold. Basically, it's learning a field pointing towards the high density regions. And that's what this means, right? It says the vector from reconstruction to input, reconstruction minus input, is in the direction of increasing density. And this P here is not the true density, it's the density estimated by the model. Now you're going to tell me, what is the P for these models? What is the density? Okay, so in some special cases of denoising autoencoders, we can actually connect the training criterion and everything for the denoising autoencoder to an energy function corresponding to a particular density, which turns out in sort of the usual sigmoid affine case to be essentially a Gaussian RBM. And Pascal Vincent showed that about 2 years ago. The equivalence, yes, and the connection is also through something called score matching, which I will explain in a few slides, which is again some alternative principle for training models, which is not maximum likelihood. And I'll say more about that. Right, it turns out that when the amount of corruption noise goes to 0, then you have exact score matching, and when it's not going to 0, you have something we call regularized score matching. Now, one of the good things there are several good things about the denoising autoencoder. One of them is, compared to RBMs and Boltzmann machines, you don't have any partition function to deal with anymore. You're still modeling the input density somehow, but you don't get any partition function. A practical advantage is you can now measure what you're trying to do. You can monitor training because you can measure reconstruction error. Whereas when you train an RBM or something like that, that has a partition function, you can't actually measure the thing you're trying to optimize. And for anyone who's trying to do, iterative optimization of some training criterion, it gets really hard when the thing you want to minimize, you can't monitor during training. So this is a really nice practical advantage. Let me skip this one. And let's go straight to try to understand how this relates to manifold learning. I mean, another way in which it relates to manifold learning. So I've explained here that it was learning the direction in which the density was increasing. And what I'm going to tell you now about is how it's actually learning about the local structure of the manifold and in which direction the manifold allows you to move around a particular point. So let's assume again that we have this simplified picture of examples sort of laid down on some low-dimensional manifold. And we have an example here. And the training criterion is going to have essentially two parts. One which is going to say minimize reconstruction error, and the other which is going to be some kind of regularizer. So now this is going to be more general than the denoising autoencoder. It includes sparse autoencoders and includes the contractive autoencoder I'm going to talk about in a couple of slides. And the denoising autoencoder turns out to be very similar to the contractive autoencoder. I'll show that later as well. So in general, you can think of there are two forces at work here. One is minimize reconstruction error on the training examples, and the other is some kind of regularizer that prevents the encoder from doing anything. It wants the encoder to do nothing, to be insensitive to the input, right? So what's going to happen here is that if we consider the kinds of changes your example could have in the direction of the manifold, in other words, like moving to a neighbor that is also a training example or a high probability point, because we want reconstruction error to be low, we want to make sure that our representation for the output of the encoder is going to be different for this guy and this guy. Like if the encoder doesn't make a difference between an example and its neighbor in a training set, then it won't be able to distinguish them during the reconstruction as well. And so you'll make that much error in reconstruction error. So in order to minimize reconstruction error, it needs to make sure that the code, the representation you learn, is going to be different from an example and its neighbor. On the other hand, if you consider changes in this direction, the autoencoder can basically ignore those variations. It's like PCA, right? PCA is choosing to represent changes in the direction where there's lots of variance, and it's throwing away information about the variations in directions orthogonal to those high variance directions. So the same thing is happening here, except because it's a nonlinear model, you'll be able to do some kind of nonlinear PCA where you don't have to choose the same directions everywhere. So basically during training, what's going to happen is it's going to throw away information about the changes orthogonal to the manifold. So that's a sketch, of course. There is an algorithm that does that quite explicitly, which we worked out last year, called the contractive autoencoder, and there's already like 3 or 4 papers about it. I guess there's one missing at the last ICML, so it would be 1, 2, 3, 4. And so the story is this: we're going to have the usual reconstruction error we're going to minimize, and we're going to add a term. So our regularizer, which is going to prevent the autoencoder from learning the identity, is going to be this explicit thing. So what is this? It's the Frobenius norm of the Jacobian of the encoder with respect to the input. In other words, it measures how sensitive is each of the hidden units, each of the features you have learned to each of your inputs. So for the jth feature and the ith input, this is the first derivative, and then we square that, sum over all the pairs of inputs and outputs, and have a scalar weight which tells us how strongly we want to penalize the sensitivity of the representation to the input. So if we listen only to this guy, we'd like the representation to be 0 or any constant. And of course that wouldn't be very satisfying, but you also need to minimize reconstruction error. So this is saying we want the derivative of the features to be as small as possible in all directions. But this guy is going to say, well, we can throw away all the directions except those I really need to make my reconstruction error small. And the only directions that are left out, that basically those you actually need here, that you don't need to squeeze to 0, are the directions corresponding to the local changes on the manifold, the local tangent plane of the manifold. So to see better what this is sort of numerically, for example, in the standard case where the encoder is just the usual sigmoid of b plus wx, then the first derivative squared would be the feature squared times 1 minus the feature squared times the weight squared. And so this is going to be minimized. So if you think about it, what does this mean? Well, we have like the usual w squared term, which you can think of as the usual L2 regularizer, but which was trying to make the weights small. But then this guy is trying to make the weights large, because to make this small, because this is the output of the sigmoid, you want h to be either 1 or 0, which means you want the sigmoid to be saturated. And saturated happens because the weights are large or they are well aligned with x. Okay, so let's try to get a geometric picture for what is going on here. And you can draw the same picture for sparse coding, actually. So what's going to happen is, to simplify matters, you can think of it like this. Some of the units are going to be responsive to the input. In other words, their first derivative is going to be far from 0. And some of the units are going to be saturated. So when hi is close to 0 or close to 1, the derivative is close to 0, and the hidden unit just doesn't respond to x. In other words, if I make a small change in x, h doesn't change because it's already in the saturation region where it's either 1 or 0. So we have two kinds of units, those that are essentially saturated and those that are not. I should have put a sigmoid here, so you're either in the flat region or in the middle region where it's kind of linear. So when it's kind of linear, it responds, and we say it's active. In the case of sparse coding, it's when the unit is non-zero. So if you look at a particular point in input space, so this is, let's say this is input space. Again, I'm going to show a manifold here. In input space, there will be a subset of the hidden units that are active that can respond to that, which means that if I consider small changes of my hidden unit, these different small changes of my input, these different hidden units will respond, and so that change will be represented by small changes in those hidden units, whereas the other hidden units won't respond at all. Yes?
Do you have difficulty in the supervised fine-tuning because you're saturating so many of the units?
You could think so, but not at all. And I had a little slide yesterday, I think, about this. When we used a rectifier nonlinearity, you actually have complete 0 of the derivative for many of the units. All of the same thing, you have active units and inactive units. The inactive units have a derivative of 0 because the response is like 0 and then the identity. So in the constant part, the derivative is 0. And for these nets, as well as the rectifier nets, it means the gradient is going to be 0 for many of the hidden units, and of course they are parameters. But that's okay. That's okay because there are other hidden units that are active, and so they'll take the credit for the current error. And in fact, the training will work quite well, probably better than if all the hidden units together were trying to explain the current error. So let me get back to this picture. So now I was looking at one example, and I said, a few of the hidden units are active and can respond. In other words, that if I move around in input space, I get some small changes of these units. And there's a region in input space in which it's the same set of hidden units that are responding. And then at some point, if I move too far away, there'll be maybe one of those become inactive, or maybe one that was inactive becomes active, and I have a different set of hidden units that are active, but they share most of the subset. And so you're going to have these different regions corresponding to different subsets, and those subsets mostly overlap. And we call these subsets, we call these regions local charts, and this is a terminology coming from manifold theories. And basically they cover the input space. Now, the important thing is these different regions, you can think of like little local PCAs where you have a different set of filters or eigenvectors corresponding to each of these regions. But the important thing is that they don't have a separate set of filters for each region. They share a global set of filters, and each of them is using a subset. I think that's a very important characteristic of these, all of these models. Yeah.
So this, it's hard to reconcile this with the picture of multi-clustering you mentioned earlier.
No. It's totally in, because what happens is you get a different subset, but you know, the same filter can be used in many different places, because they share. You can think of there's a pool of hidden units, a pool of filters, and depending on where you are, you look at a different subset, but the same feature is active in many places. So like if your sparsity level is 5%, it means that each feature is active 5% of the time. So it like in my example with multi-clustering, it would be that you have these half planes where 5% of the time you're on the one side and 95% you're on the zero side. But still, 5% is large. And when you compose all of these things, you still get an exponential gain. So it's like in sparse coding, if you only have one unit active, it's like k-means, you don't get the exponential gain. But if you have k, you get power of k gain in terms of representational power. Yeah?
What happens if you get a sample that is outside all those charts?
Well, no, there's no such thing, right? I mean, there's always a subset of hidden units which will be active. So what I was trying to show here is what's happening here near the manifold where the data concentrates, but there'll always be some units responding, right?
Even outside, so far away.
Yes. Okay, now so we did some experiments to actually validate that this was happening. And so what you can do is look at the Jacobian matrix dH dx. So this is a matrix, right, dH dx. And to understand better if there was really some directions to which the hidden units were sensitive and other directions to which they were not, we actually look at this Jacobian and look at its singular values. So these are singular value spectra of those Jacobian matrices of what has been learned for particular examples. So for each example, you get a different Jacobian matrix. And it's hard to visualize these matrices, but it's easy to visualize their spectrum. You can do an SVD of the matrix, and then you order the singular values with the largest first, and then you can just plot these spectra, which are telling a lot of information. What these spectra tell us is that there is one direction for any particular example in which the hidden representation responds basically like preserves all the information. So one here means essentially that there's a vector in input space whose norm is perfectly preserved in representation space. Whereas if you had like 0.01, it would mean that if you had a vector of norm 1 in input, after mapping it, you'd get a vector of norm 0.01. So it's how much it squeezes information in different directions, and this corresponds to different directions. Now the directions are different depending on where you are in input space, but you can still average the singular value spectrums to tell you something about the dimensionality of the space. So what this says is that basically for this data, which are CFAR10 little images, something like 50 or 100 or 200 dimensions are enough to capture, at least by this model, the variations that are present in the data. This is using, the red one is using a contractive autoencoder, and this is using a regular autoencoder with sort of standard regularization like L2 regularization or no regularization, which is essentially the same. And we've tried the contractive autoencoder on a bunch of data sets. So these were early experiments where we compared to some benchmarks that we did several years before on variations of MNIST and sort of little geometric images classification problems on which a bunch of deep learning methods like autoencoders, RBMs, denoising autoencoders have been tried. And one here means one layer, two layers. So RBM3 here means like a deep belief net with 3 RBMs. And the contractive autoencoder was doing quite well. Actually, it's doing even better than that. So we've used the contractive autoencoder in this competition, the transfer learning competition I was mentioning yesterday, and helped us to win 2 of the 5 entries. Okay, so let's try to understand better this tangent plane story. Visualizing things a little bit. So MNIST, easy to understand what's going on. We have digit images. And now what we can do is look at this Jacobian. Before I was looking at the spectrum. So it tells us something about the dimensionality that is preserved by the model at each point. It tells us about the dimension, the number of directions that it preserves in the representation. But we can also look at these particular directions. At a particular point, we get a set of active units, or we get a whole Jacobian matrix. We can look at the leading singular vectors for that particular input example, and we can just plot them because they turn out to be images. And so what does this mean? The way to understand this, so these are, each of these is a vector in the same space as the original input, and together they form a basis for the tangent plane of the manifold as estimated by the model. So you can think of, if you take your original image and you add a little bit of some of these, or actually any combination of these, you get other images which the model thinks are likely. Right? That's what it means. In fact, we'll be using this, exactly this, to sample from the model. So once you understand that this is what the model has figured out, well, you can actually go ahead and take an example and take some small random convex combination of the local tangents, add them up, and you get a new sample dreamed up by the model. And in this way, as we'll see, you can sample from the model using some Markov chain. Okay, this is another example. What we see in these, so trying to understand what these look like, basically what they mean here, this one is saying like shift to the right. And you can see like here, maybe move the bottom part, this is moving the left and the right here, and they're pretty easy interpretation. So this one is like, some of these are moving the loop of the 2, and others are moving the top part of the 2, and things like that. So very reasonable thing you would expect if you have a digit in terms of the transformation. So it's not just the usual geometric transformation. You can see they are specific to the image. Like in a 2, you want to mess up with the loop and so on. It's not just a translation. Yeah?
Does each image correspond to a hidden unit, or is it corresponding to the basis vector?
They're the basis vectors. Now, to first degree, you can think of them as hidden units. But because these are actually soft, they're not hard saturating, and because the hidden units are not ordered in sort of magnitude, it's more convenient to actually do the SVD and look at the leading ones to make sense of what is going on. But sort of to first degree, it's good to think about it as these correspond to the hidden units which were active. In sparse coding, that would be explicitly the case. But in the way what we've done here is we've ordered them, and we've taken linear combinations that correspond to the directions of most change that the model likes. Now, this ugly stuff is what you get in terms of estimated tangents if you do what's called local PCA. So what is local PCA? Is basically like a Gaussian mixture model where in each region you do a little PCA, so you estimate the local covariance by just looking at the examples in that region. And so this is to illustrate that if you don't have the sharing across regions, if you use different filters in different regions, and you don't have enough data, so I guess CFAR10 is something like 60,000 examples, then your local estimations of the tangent planes are just wrong. So you get this mess which is useless. And if you do the contractive autoencoder, you get this, which is much better and tells things like, oh, I can move the head, I can move the legs, and things like that, which make a lot of sense. So yeah, this is just to highlight the power of sharing. In a sense, it's representing the same information in principle, but somehow the way we've estimated the parameters here, because there's sharing, is much more statistically efficient, and we are able to learn from a limited amount of data, which you can't with a local PCA because it doesn't have that sharing. Now, there is a nice connection between the contractive autoencoder and the denoising autoencoder. And here's the gist of it. If you consider a denoising autoencoder where I'm just going to use a little Gaussian noise as the corruption. So I take my input, x, I add a little bit of Gaussian noise, I reconstruct, and then I compare with my original x, and I measure the loss, and I do the expectation over epsilon. And then I do a Taylor expansion of this thing. So I replace r of x plus epsilon by r of x plus dr dx times epsilon. And I expand the square. And then I throw out the high order things whose expected value, I guess, is small compared to epsilon. And then the expected value of epsilon squared is, I call that sigma squared. So that's the variance of my noise. I get this. So what is this? So on the left we have basically the denoising reconstruction error, and on the right we have reconstruction error, regular reconstruction error without corruption, plus a contractive penalty. This is the Frobenius norm of the Jacobian of the reconstruction. So this is saying that a denoising autoencoder is a contractive autoencoder on the reconstruction function, whereas the contractive autoencoder, the way we've trained it before, was contracting the encoder. But notice that there's a strong kind of connection between the two. If you contract the encoder, you're forced to contract the reconstruction as well, because it's part of the reconstruction. And in fact, in the contracting autoencoder, the way we use it, it uses tied weights. So the decoder weights are the transpose of the encoder weights, which ties the two even more. So that's interesting. At the last NIPS, we had a paper which won an award, which uses the contractive autoencoder and exploits sort of the geometric intuition behind what it's doing, and allowed us to get really good results on different data sets, including sort of the old MNIST. It exploits three hypotheses that we've been talking about. So there's the semi-supervised hypothesis, which is saying P of x, the input distribution, is related to P of y given x. So this is the thing we want to predict. The second hypothesis is the manifold hypothesis, basically that the data concentrates in a low-dimensional manifold. So we've seen these things before. The third one is connected to the second one, but in the case where you want to do classification, we're going to assume that your different classes correspond to different manifolds. In other words, there's the manifold of 2s and the manifold of 3s and the manifold of 4s. And that in between those high density regions corresponding to each class, there's a low density region, kind of void that you have to cross to go from one class to another. And that's the thing which helps us create natural classes, because you have this separation between the classes, that they're natural classes. Okay, so these are the hypotheses. We put them together into this algorithm, which we call the manifold tangent classifier, which is meant for classification but exploits the unsupervised learning of the local manifolds that I've been talking about. Once you know that a 2 can be changed in these and these ways, and for any example you know in which ways it can be changed and maintain its 2-ness, you can take advantage of that. So how do we do it? We first train a contractive autoencoder, but what we're going to do is we're going to record the Jacobian matrix for every example, every training example. We're going to record that Jacobian matrix. Actually, we're going to record its leading singular vectors. So we're going to throw away the low singular values ones and just keep the leading ones. And so that's the unsupervised part. And then the supervised part is we're going to train our predictor. So our case would be just a neural net, which happens to use those features as input. This is the usual thing we do on top of our contractive autoencoder. But we're going to do something different here, which is In addition to the usual log likelihood of classification, like the log of p of y given x, usual supervised training error, we're going to add a penalization term. There should be a squared here, which is this. It says, so if our output, if our class probability prediction is f, then we want df dx to be orthogonal to u of x, to the directions, to the singular vectors that we found in the first unsupervised phase. So what this says is I want my output probability function to not vary in the directions that I found my data to vary locally. So if I can translate a 2 and it stays a 2, I would like a translation of the 2 to mean no change in my output function. So you just add this penalty and compute derivatives, and you get good results. So we've tried these things actually on text data, on MNIST, where we got 0.8%. This was using no knowledge at all, so no convolutions, no transformations, no totally knowledge free, except for these 3 hypotheses about sort of manifold learning and a bunch of other data sets. All right, I think we are on time for our break. Thank you.